Well, OK, so I guess we can get started. Again, the beautiful acoustics of this hall. I mean, I'm not using any, I think, enhancement. So welcome to this talk on making .NET applications faster. I hope you're enjoying the conference, and I'll try to keep up the trend. We're going to talk about some best practices and techniques for making .NET applications, well, faster. And these tips and demos are built on a large body of work that you can also see in my Pluralsight courses. And by the way, if you'd like a trial Pluralsight subscription, there's a booth, and they'll be happy to hook you up with one. And there's also a book I wrote a couple of years ago called Pro.NET Performance, which might also be useful. But here I kind of try to take the whole book and the 2 courses that I have on .NET Performance and just sort of distill them into the most useful things that I could fit in 90 minutes or so. We're going to talk about reducing garbage collection pressure to improve runtime and to improve memory utilization. We'll talk about reducing startup times, which in many applications is quite critical. For any kind of client app, it's really important to reduce startup. And even for server applications, longer startup means you spend more time, not servicing requests, especially if something fails. And we'll also talk about collections, the .NET built-in collections, and how to choose some more sophisticated collections, even implement your own collections if the situation requires it. So some of these things are more basic, and some are more advanced. For example, the whole collection discussion, I'm going to go through it really briefly because I think many of you as .NET developers are already familiar with the various kinds of collections we have. But the other things could be a little more advanced. And there's one demo at the end, which if we have time to get to, it's going to be great. It's a really crazy one. My name is Sasha Goldshtein. I live in Israel. I work for a company called Sela, which is a training and consulting provider. And this is my 3rd DevWeek. I'm having fun. I hope you are too. And right after this talk, I'm staying here for another one on C#6, so you're also welcome to stay. So as I said, we're going to talk about collections, startup time, and garbage collection. These are 3 core topics, and there's lots of little things around. So let's start with collections, and like I said, it's going to be a pretty quick review. The .NET framework has a bunch of collection classes, and new ones are being added all the time. For instance, in .NET 4.0, we had multiple collections made available in the concurrency framework, in the TPL. And previously, we had additions such as HashSet, which was only added, I think, in .NET 3.5. And there's all kinds of concurrent collections being added more recently. So there's still lots of work on the .NET Framework's collections library, which sounds really fundamental, but there's still some additions going on. In addition, there are many good, even excellent, production quality libraries for .NET applications which have even more collection implementations. For example, there's the C5 library. Has anyone ever used C5? That's wonderful. So C5 is a really great library that has implementations for pretty much everything you find in an algorithms and data structures book, plus it has some specialized collections. And they usually are very rigorous about giving you, the asymptotic guarantees and sort of documenting every little detail, even better at that than the .NET Framework collections occasionally. But in any case, for all of those built-in collections and for any library you find, the fundamental operations on a collection are usually inserting elements, looking up elements by some criteria, maybe by key or some other way, and of course deleting elements from the collection. But the differences between the different collection classes, as I hope you know, are first, runtime complexity of the different operations. So how long does it take to find an element in a collection by key or insert an element in the middle of a collection? Space complexity, which means the space, the memory usage of the collection given a certain number of elements, and these vary greatly. Some collections could be a dozen times bigger than others for the same number of elements. And then we have specialized operations. Some collections make it possible to do certain things very, very efficiently, while others don't. And I'm going to show you one example of that as soon as we get through the fundamental collections, which are part of the .NET framework. We're going to take a look at an example where the operation we need is unique and is not implemented by any existing collection in the BCL, and we'll have to sort of roll our own. So let's take a look at one simple example, then review a few others, see a quick demo, and this should give us a good coverage of the built-in collections anyway. So here's linked list of T. And if you ever looked at the structure of a linked list, specifically the .NET implementation at runtime, it's a pretty big object. It's got lots of little objects inside, but each object is pretty big. So this is a typical node in a linked list of T, the .NET class. It has a couple of overhead fields which are there regardless of the type of object you're allocating. This is the overhead that every .NET reference type has. So we're not going to go in depth here, but these are the object header word and the method table pointer. And for instance, on a 64-bit system, these are 16 bytes together. And then we have the next and previous nodes, the links, I mean. And again, on a 64-bit system, each is 8 bytes. So these are another 16 bytes. And then finally, we have that, the data that we want to store in the linked list. And if you're storing, say, ints, then each int is only 4 bytes. So this whole thing is going to be 36 bytes on a 64-bit system. And only 4 of those bytes are the actual data that you put in there. So there's definitely something interesting if you look at collections from a space complexity perspective. And I'm going to show you a very quick demo just in a moment. The other things, the other operations are pretty quick. So it's really easy to insert and delete elements because you always have these links between the nodes. But lookup is slow. There's no built-in way to index into the collection to find an element by key. You just have to go linearly through the whole thing and compare whatever you're looking for. The other kind of collection, which is a foundation for lots of others, including one we're going to build together, is, of course, the built-in arrays. And arrays are great. They're flat. They're sequential, so all elements sit together in memory. However, they are statically sized, so you can't add or remove elements anywhere. You can just change the existing ones. It is almost an immediate operation to access an element in an array by index, which is something you can't do with a linked list. And there is, again, no overhead for the array elements. So if you have an array of 1 million ints, you can very quickly just, you can in very little space store those 1 million ints. You're not wasting any space on object overhead, nodes to the previous and next elements, and so on. So let's take a look at a really, really simple demo, which tries to compare two very fundamental operations on arrays and linked list. So what I'm doing here is basically creating an array of a certain number of elements and creating a list, a linked list, with the same number of elements, and then measuring the time it takes to sum all the elements in both collections. So here's one loop I'm measuring. It just goes over all the elements in the array and sums them up. And here's the other loop I'm measuring. It goes over all the elements in the linked list and sums them up. So I hope you all expect there to be a certain performance difference because I've just explained how lists are big and wasteful and there's links going here and there. And it's so much more efficient to use an array. But how many of you think it's going to be a significant difference, like a big, big difference? OK, so I phrased the question correctly. Let's run this thing. It does lots of iterations to make sure there's no weird outliers. And it takes almost 3 times the time to sum a linked list than an array. And it's not like there are more operations involved. It is the memory structure. It is the space complexity that kills us here. If you look at the generated assembly language, if you're the kind of person who likes to look at the generated assembly language, you'll see the basic operations are pretty much almost the same in both cases. But it's the fact that you have to touch more memory that's killing us in the linked list case. You have to touch more memory, which means you have to go to memory more often, and the cache doesn't help you as much. If you'd like me to go into more detail, please feel free to ask me later. But for now, let's just agree that space complexity matters. So not the only I mean, you should be looking at more than just the O of whatever guarantees for runtime complexity. You should also be looking at space complexity as a criterion for your collections. And arrays are often really good at this. Right? Arrays often beat other collections in space complexity because there is no overhead except for the array elements and a tiny, teeny header that the whole array shares. It's not a per element overhead. So anyway, that was just a quick demonstration of space complexity. I would like to also show you an example of how the different collections differ in terms of runtime complexity, which is going to be more obvious. But still, it's important to see just how big this difference can be in terms of running time. So I'm going to skip ahead a little bit to trees and hash tables, just again to give you a quick coverage of those. We have a couple of collections in the .NET framework which are based on binary search trees. Specifically, the .NET implementation uses red-black trees, if you recall from school or an algorithms book. There used to be implementation based on AVL trees, but red-black trees are pretty much the state-of-the-art for binary search tree collections today. For example, the C++ standard library uses red-black trees as well. And so sorted dictionary and sorted set are just trees like that, and they give you fairly efficient lookup by key, and also they are sorted by key, which is something extra, right? I mean, we talked about space complexity, we talked about runtime complexity, but the fact the elements are sorted just comes extra. It's just another property of the collection, which we occasionally might need. All the fundamental operations on trees take log n time, log-based 2, which means really little time in most cases. So for instance, log-based 2 of 100 million is just a little less than 27. So, 27 operations in the tree for a tree of 100 million elements really doesn't sound like a lot. But it still does matter if you have lots of these operations, and I'm going to give you a quick demo comparing trees to hash tables on the next slide. One of the key problems with trees is that you still need lots of space for each element. So each tree node has a link to the left child and the right child, plus it has a link to the parent in the .NET implementation. So that's 3 pointers already for each node. 3 pointers, that's 24 bytes on a 64-bit system. Plus, each node is a reference type. So you also have 16 bytes of object overhead. So that's already 40 bytes of overhead. And then you have your elements. And then you have the stuff you want sitting in the tree. So that's lots and lots of space that's wasted. And again, if I were to implement some kind of algorithm that goes over a tree and sums all the elements, it would have been, again, much slower than doing the same thing with an array because of this whole sequential property that arrays have. So the other kind of associative collection that we have in the .NET framework are hash tables of various kinds. So we have dictionary of key value, hash set of key, and we also have the hash table class, the old one, the non-generic one, which no one should be using anymore, but it's still out there. And these classes are somewhat more complex internally to describe. They use a variety of arrays to store the data. There are also some linked lists inside. So it's harder to estimate exactly how much space you're sacrificing for the more efficient operation of those collections. It's probably somewhere between a tree and an array, probably closer to a tree. So you're spending quite a bit of overhead for each element still in those hash table-based collections. In terms of runtime, however, you have insertion, deletion, and lookup in constant time. And that sounds like a great property, which it is. It does require some discipline from you as the developer. You have to make sure some constraints hold for your hashing function, for your get hash code implementation. We're not going to go into detail here, but assuming you've got that right, or you're using a common type as the key, such as a string or an int, other primitive types, assuming these hold, you get a really efficient collection in terms of lookup and insertion and deletion. The one thing it does not guarantee is sortedness. It is not sorted by anything. which could, in some cases, be important. So let's take a look at a quick demo, again, just to see how big the difference can be between logarithmic time operations, hash tables, which are sort of the best, and linear time. So again, I have a very simple demo just to drive this point home, which searches a range of elements for a specific element which isn't there. So in one example, I use array index of. That's one benchmark. An array index of takes an array and an element and tries to find that element in the array by just going over all the elements one by one. And that's linear search. That's going to be the slowest one. Next one we have is binary search, which is essentially what happens in a tree. Obviously, it's not a tree, but it's kind of similar. If I have a sorted array, then I can use a binary search to find an element in that array. And finally, the last benchmark here uses a hash set. So we put numbers in a hash set, and then we try many times to find an element in that hash set. In all cases, I'm looking for an element which isn't there, which in most cases is the worst case. For example, for linear search, it's obviously the worst case because you have to visit every single element and see that it's not there. So if I run this benchmark again, you probably expect a huge difference between linear search and binary search, but the extent of the difference between binary search and a hash search could be a little more surprising. So I'm not going to ask you to guess. I'm just going to show you the benchmark results. But I think it's instructive to, at least show it to you once. So for linear search, I actually perform 100 times fewer iterations than for the other benchmarks because it is so slow. It takes almost a second on average, and it does 100 times less searches, fewer searches. But the binary search and the hash set search are pretty interesting because you can see there is an order of magnitude difference here, right? So that's logarithmic scale and constant scale, which the hash set provides. And so they're both really quick, right? They search for an element many, many times, and still it takes only a millisecond or less than a millisecond. But these things add up. And so even for these kind of differences, even to these kind of differences, you should be paying attention in your design. So these are all the built-in collections. And I've demonstrated, I hope successfully, that space complexity matters and runtime complexity matters. And with that said, let's think about custom collections, situations in which there is no built-in collection that quite satisfies our requirements, and it's worthwhile for us to pursue a custom implementation. And why would we need a custom collection? For pretty much the same reasons, for the same reasons we go with one collection or another. We might need specialized operations, which no built-in collection provides. For example, suppose the .NET framework didn't have a sorted collection at all, and you needed, for some reason, to store sorted elements in your application. So you'd obviously have to go and implement some kind of sorted collection yourself. And the other reasons are just time and space. You might need very efficient storage for your data, or you might need very efficient operations, accesses, lookups, insertions, whatever, for your data. So here's one example which I really, really like. It's a very cool collection, which is also very, very simple to implement. It's like 50 lines of code. Well, obviously, it can be optimized, but it's 50 lines of code, and it's really great. So the problem is as follows. We're trying to implement a text editor together. And the text editor needs to store a dictionary of words. But it's a text editor, so to do spell checking right, it also has to store a bunch of suffixes. So run dolphin and regard, but also running dolphins regardless, and maybe some other invalid forms like regardlessly and regardly and regards and so on. Regardness, maybe. So we need to store a dictionary of words for spell checking, but we also want an IntelliSense-like completion facility. So if the user types dolph, we'd like to offer a list of completion options. So we need some way of searching words by prefix, right? So two basic operations are required here. First, spell checking. So we need to check if a word is in our dictionary. And two, we need to find all the words which are prefixed by another word that the user has already typed. If you think about this, I mean, there are some collections which seem to be appropriate, like maybe a hash table of some sort, or a tree, but there isn't quite anything that satisfies all of those requirements. Which one would you say is the best fit for this problem? I mean, how many of you would use a hash of some sort? No? No one wants a hash? OK. How about a sorted dictionary, a sorted set, something like that? Yeah? OK. So a few of you. OK. And the rest are undecided. That's fine. Or maybe you're thinking some other data structure altogether. Now, you should realize if we only have like a dozen words, then we could just store them in an array and do linear search. But if we have a few million words, which could be the case for English with all the various suffixes and proper names and stuff, then it could be really, really slow to just go over the whole collection every time. So I'd just like to criticize the two approaches I've just mentioned. HashSet could offer very, very fast spell checking, right? So we put all the words in a hash set, and then we just check if a word is in the collection. That's crazy fast, constant time. It's the fastest approach we've seen before. But it's not sorted, a hash set. So it's kind of unobvious how we'd find the prefix thingy. So given a prefix, how do we find the words which this prefix completes? So a hash set has this issue. In a sorted set or a sorted dictionary, we have logarithmic time access, which is decent. But unfortunately, sorted set, the .NET implementation anyway, doesn't really give you in a trivial fashion successor and predecessor iterations. So it's not really trivial to go from a word to the word, I mean, to go from a prefix to the words it is a prefix of. And although it could be made to work with some effort, or maybe by implementing your own tree-based collection or borrowing a tree-based collection from elsewhere, you'll see that there is still a better option, which is even faster. And that option is called a trie, T-R-I-E. And a trie is a really simple data structure. You're going to laugh, it's so simple. And again, it's 50 lines of code to implement this thing. It's basically a tree where each node has 26 children. So this is the root of the tree. And it's got 26 children, one for each letter. English has 26 letters, right? I think so. So 26 letters, 26 array elements, 26 children. Now, say we have the letter P over here, so the index for P in the array points to another node in the tree. And that's the node for P. Now, this P here has 26 children as well. And the A over here points to the PA node, right? So you see the path is shaping up the prefixes. The PA node from L has a reference to a PAL node, and the PAL node from M has a reference to the PALM, palm node, and from E to the pale node. And the nodes, which are really words, which represent words, are marked as such, right? So this thing over here, this border, indicates that this node is a terminator, is a word terminator. That's the whole data structure. So by following paths between nodes, you form a word. And if you are at a given node, finding all the words which it is a prefix of is really easy. Given a node, you just follow the references till you reach all the terminators. That's all there's to it. Now let's think about the complexity here. So suppose I have a word of length 500, and I want to find if it's part of the tree, if it's part of the trie, really. So how many operations is it going to take? I have a word of length 500. I want to see if it's part of the tree. What's the upper bound? OK, so let's think what we'd have to do, right? So suppose the word starts with a P. So we go to the P node from the root. And then suppose the next letter is an A. So we go to the PA node from the P node. And then suppose the next letter is an L, so we follow the L link to the PAL node, and so on. So for each letter, we follow those links. So what's the maximum number of operations for a word of length X? X, yeah. So we either fail to find it earlier, or we reach a terminator after traversing X links. So this is really as fast as it gets. I mean, you just sort of go over the word, and you traverse try nodes as you go. And indexing those arrays is a constant time operation as well. They have 26 elements, and they are arrays. So I can just take the letter from the word and see which array element I should be dereferencing. So looking for a word is really trivial. Sort of constant time, I'd say. So it doesn't depend on the number of words in the try. And how about prefix search? When I've already mentioned this, if I want to find all the words which PAL is a prefix of, then I just go to the node PAL, and then I start traversing all the links from PAL. So just trying to reach all the words which are reachable from PAL. And those are the words that PAL is a prefix of. So this is also a very easy, simple operation, very fast operation. In addition to those advantages, this thing, which might not look very compact, is actually pretty compact on space. Because shared prefixes are only stored once. So for the words pale and palm, you only have the PAL part once in the tree. There is just one node representing that shared prefix. So you're storing, in some cases, actually less data than if you just had a collection of all the possible words. Problem is, you have to construct this thing. Constructing it from a dictionary could take a while. But if you're doing a text editor, right, constructing the tree, you do it once on startup. And you can do it in a background or something. And then you can start spell checking and suggesting and stuff. So the initialization isn't that bad. So let's take a look at how it fares compared to other options. I have here an implementation of a try. Like I said, the whole thing is, well, 100 lines of code, including using statements and namespace prefixes. It obviously could be optimized a little, but my implementation is extremely simple. It just goes, we have a class node, and then node has 26 children, just like I said. And then I have a bunch of operations on those children. Now, it could be improved by using sparse storage, for example, because in many cases, you don't really have 26 children. You usually have much fewer than that. But I mean, even in this shape, it beats the other options. So what my measurement program does is the following. The operations themselves are just constructing the collection. So constructing the try, or constructing a sorted set, or constructing a hash set, and then doing lookups, looking up a word and looking up words by prefix. So these are the operations we measure. So I'm going to run this thing, and it's going to take a while to build the try. True, it's going to be at a disadvantage there, but the other operations are going to be pretty nice. So OK, so we've got the try done, and now we're measuring the sorted set. And next up is hash set. OK, so let's take a look at the key operations. Creating the try took 2.7 seconds on average, and the dictionary is about 5 megabytes of English words. So it's a pretty typical set size. So 2.7 seconds to construct the try. Constructing a sorted set with the same data takes just over a second. And constructing a hash set with the same set of data takes 0.3 seconds, which is really nice. But I mean, again, the data set construction doesn't matter as much to me. The other things do. So looking up a word in a try takes 21 milliseconds on average. In a sorted set, it takes almost 2 seconds on average. And in a hash set, it takes 41 milliseconds on average. Obviously, it's not for one operation. I have many iterations to sort of beef this thing up. But there is still a considerable difference between a try and a hash set in terms of lookup. And I mean, a hash set is crazy fast. It's constant time. And still, the try bits it in raw lookups. And for finding words by prefix, I'm not even comparing the other approaches because they'd have to be linear time for the .NET implementation anyway. So I'm only giving you time quotes here for the try. And the reason it looks weird, short word prefix and long word prefix, is that shorter words have more, shorter prefixes will produce more words as a result. So it actually takes more time to generate that collection. But in any case, just to show you the number of operations we're going through here, so for long word prefixes, there it is, we're doing 10,000 operations, 10,000 lookups in, what was it, 300 milliseconds or so, right? 10,000, there it is, 10,000 lookups in 200 milliseconds even. So it's still incredibly fast, definitely not linear time, not even logarithmic time. It's incredibly fast, and it's really the only collection which really, really works well in this sort of scenario. And it's a custom one. I mean, there's nothing like it in the .NET framework, and I don't really see one being implemented anytime soon as part of the .NET framework. So I hope this convinces you that performance, you can often find performance in data structures and collections. So all of this stuff you learn at school can be really valuable occasionally, depending on the problem you're trying to solve. By the way, tries are pretty standard. They're covered in lots of literature. OK, so our next third of the presentation is going to be focused around startup time. And by the way, if you have any question or anything troubling you, please do feel free to interrupt. It's fine. OK. So we're going to talk about startup time now, improving startup time specifically. And like I said in the beginning, for many kinds of applications, this can be really critical. And even shaving off like 25% of your startup time can be really, really great. It can save lots of pain for your users, for clients, for production servers. It almost doesn't matter what kind of application you're building. You can save lots and lots if you reduce startup times. So I'd like to show you several techniques for this. Some are more approachable, so you can try them out really quickly, and some require significant investment, but you should know your options, really. So what are the startup costs that we're trying to optimize here? So for cold startup, from my experience anyway, most, if not all, the cost is disk I/O. You're reading from disk your code, your data, your working set, and that takes, well, most of the time, anyway. Even if you're using a fast disk, SSD or flash storage or whatever, still, cold startup is usually dominated by disk I/O. And so that's the first thing to improve, to try and reduce the I/O you're making against the disk if you're dealing with cold startup times. And by cold startup, I mean, of course, first-time startup. The user has just turned on the computer and launched your application for the first time. Warm startup, which is not the previous case, which is the case when the user has already launched your application and now launching it again on the same session, warm startup is dominated by a bunch of other factors, usually. Disk I/O is no longer a concern, usually, in warm startup. Why? Why is disk I/O usually not a concern? What? Windows caching, right. So the operating system can usually cache file accesses for the next time you need them. And so launching your application for the second time can be almost instantaneous in some cases. Visual Studio is a good example of this. Launching your first Visual Studio, right, is really horrible. But then adding 5 more instances is almost instantaneous. So warm startup is usually dominated by just-in-time compilation. So you launch your application, and the code has to be compiled. I'll remind you that later that .NET code is compiled in two stages, and part of the compilation has to happen at runtime. So that's part of the startup phase. For older versions of the CLR, there's also signature validation if you have strong named assemblies. This is not performed anymore for full trust, so for most of you it shouldn't be relevant anymore. But there used to be a pretty expensive signature verification step which happens during startup. There's a Windows thing called DLL rebasing, which happens when multiple libraries collide and want to be loaded at the same memory address. This is also less the case for .NET applications anymore. And finally, there's, initialization, the stuff you do during startup. So reading stuff from the database, initializing your in-memory collections, whatever it is you're doing, creating your UI, of course. So these are the costs that we're trying to reduce. And lots of effort should be placed in the cold startup costs to reduce I/O, because that's the thing that often takes seconds or even dozens of seconds. So we have several approaches. Some are more familiar, some are newer. The easiest thing you can probably try is NGen, native image generation. I assume some of you have already heard about this option. There is a tool that ships with the .NET framework from day one. It's not new at all, which is called NGen. And it can pre-compile your .NET code. It can take your exe and your assemblies, your DLLs, and pre-compile them to machine code before you run your application. This can be done in advance, and then it's cached on that machine forever. So you can only do it, you can do it safe during your installation process, at the end of your installer, and then the user has a cached version of your pre-compiled code on their machine. And so you can at least save the just-in-time compilation costs every time the user restarts your application. And this is so useful that Microsoft is using it, for example, for the entire .NET framework. When you install the .NET framework, anyway, up to .NET 4.5, part of the setup process is NGen, does NGen. It precompiles all the .NET framework assemblies so that they at least can be already native. So it's really easy to use NGen. You just run NGen from a command line and you give it your exe and it just finds all the dependencies automatically and does its magic. The cool thing is it doesn't change your files. It only stores the precompiled version in a separate folder, and it doesn't affect your original code, your original files in any way. And if you want, you can always roll back. So again, it doesn't modify your sources, obviously your sources. It doesn't modify your binary products on that machine. On Windows 8 and CLR 4.5, which were announced a couple of years ago, Microsoft has made this process even better by doing NGen automatically. So there is a process, a maintenance task, that runs in the background and tries to detect which assemblies are taking long to compile. And then these assemblies are being NGened, they are precompiled in advance, and other assemblies which aren't so useful are not. And apart from this being automatic, which is pretty cool and useful, it's also nice because it discards unused assemblies, which saves disk space. So if you have a tablet with 32 gigs of disk space, you really don't want it wasted by native code which you're not using anymore. So the maintenance task can also remove unused native images. So NGen is pretty great, and I'm not going to show you a demo, but you can definitely try this at home if you're dealing with long startup times. It can reduce JIT compilation costs to 0, and it can also help with reducing I/O, because these native images, in some cases, can be smaller than the original code. Another thing, which is much newer, and it was added in .NET 4.5, CLR 4.5, is multi-core background JIT. The idea here is that instead of waiting for a method to be invoked and then compiling it, the CLR can, in advance, try to guess which methods you're going to need and compile these methods, again, in advance in a background process, a background thread, to be more accurate. So the JIT can now, if you let it, run in the background while your application is starting up and compile methods before you even need them, compile methods before they're being called. Again, this is called multi-core background JIT. That's the marketing term. It's all in the system runtime profile optimization class. There's a couple of really simple methods that you call to instruct the CLR to use this optimization. So you can tell the CLR, I would like multi-core background JIT enabled. This is enabled by default in ASP.NET as of 4.5. So if you're doing web development, IIS, ASP.NET, you should be already making use of this. But for any other kind of application, you have to opt in to ask for multi-core background JIT. Now, this isn't a lifesaver, but it can definitely reduce startup by a few percent, maybe a couple dozen percent in pathological cases. But I mean, these things build up, so you shouldn't dismiss it anyway. It does require 4.5 at least. Next thing you can try, and this is something you're going to be able to try by default in just a couple of months, is ReaJIT, which is a huge project, a huge undertaking at Microsoft over the last few years, where they took the just-in-time compiler and rewrote it from scratch. In fact, it wasn't a rewrite. It was kind of like a new project. They just started building a just-in-time compiler from scratch. And one of the key reasons why is that they wanted faster startup. They wanted faster compile times. They wanted the just-in-time compiler to speed up your application startup. And so in some cases, ReaJIT can, again, shave off a couple dozen % of your startup time. In pathological cases, in this chart, could be a 5-time or a 10-time difference using ReaJIT or using the older just-in-time compiler. Now, it's not out yet. It's in preview right now. It's in a really advanced preview stage, but it's not out yet. You can test it in production if you'd like. And I've seen it improve startup performance in production, although it's sometimes a little hard to convince people to use this kind of thing in production, but it does improve startup times in production. For example, is anyone using RavenDB? No, it's a NoSQL database, which I have a talk about tomorrow. So anyway, Raven, for example, the startup time for Raven went in one of my tests from 2.5 seconds to 1-point-something seconds. I don't remember the exact numbers, just by switching to ReaJIT, so just by saving on this just-in-time compilation costs. And ReaJIT, again, it's in preview right now, but it's going to be part of Visual Studio 2015 and of .NET Framework vNext 4.6, whatever it is. So in the next CLR, in the next .NET Framework, in the next Visual Studio, we're going to have ReaJIT by default. And then, again, this is something that could already help you today, but will definitely help you in the future, will hopefully help you in the future. Next thing you can try is a set of tools that are strictly about reducing I/O. And there's a couple of them that I'd like to mention here and show you an example of one of them. One tool is ILmerge. Has anyone used ILmerge before? Yeah? Oh, OK, a few of you. So there's a bunch of reasons to use ILmerge, but the one I'm talking about here is to reduce the number of assemblies that have to be loaded from disk and the amount of disk I/O that has to be performed in general during application startup. What ILmerge does is take all your application's assemblies and just pack them up into your executable. So you take a.dll and b.dll and c.exe, pass them through the ILmerge pipeline, and you get a single exe, which is, of course, bigger, but you don't need the individual assemblies anymore. Now, other reasons to use ILmerge is that it gives you a single executable deployment plan. So your whole product ends up as a single exe, which you can easily copy around, and users aren't exposed to all the different assemblies you have. And this can be done after compile, so it doesn't affect your sources. You just take the products directory, run ILmerge, you get one exe which you ship. Now, this can be good for startup times because reducing the number of assemblies means you're accessing fewer files, and in some cases, you're actually accessing fewer pages on disk. In addition, there is a constant overhead for loading an assembly, which is always there in the CLR. So the fewer assemblies you load, potentially the faster your application will start. And from the framework's perspective, this whole thing, the merged executable, is a single assembly. It does have the internal structure which your original code had, but it's a single file on disk. And so I have here a really contrived example which shows how ILmerge can be useful. I have an exe and 200 tiny assemblies, which this exe depends on. And then I run ILmerge to merge all these 200 tiny assemblies into a single bigger executable. And the startup time difference, this is cold startup. And the reason I'm showing you this canned demo is because I can't easily reproduce cold startup without doing a full machine restart, which I'm not going to do right now. So the canned results are 800 milliseconds before the merge and 650 after the merge, which is pretty decent. And this application doesn't do much except for instantiating a type from each of those 200 assemblies, just to demonstrate the performance difference. But it still kind of proves that there are some costs here that can be offset by merging. So merging is another thing worth trying to reduce startup times. Another approach, which I've also used occasionally in a distant past, is going the way of executable packers. There's a bunch of tools which can take your whole application, again, including your dependencies, including all the assemblies that you use, and package that thing up into a compressed binary, which takes less space on disk. And because it takes less space, it can be loaded more quickly from disk. So basically, you're trading storage, you're trading space for CPU work, because once you read that file from disk, you have to decompress it. You have to open up the compression. So there's a bunch of tools that, again, I haven't used any of them recently, but there's a bunch of tools that claim to be able to take a .NET application and package it up as a compressed executable that isn't itself a valid assembly, but it can be, at runtime, decompressed to one. Some of these tools can also do obfuscation for you. Some of these tools can also encrypt your code. So there's a bunch of related capabilities. But for performance, you're specifically looking at compression. So you want tools that can take all your dependencies and compress the whole thing so it takes less space on disk. So one I've used relatively recently is RPX, which is an open source tool. And it worked rather well for a Windows 4 application and reduced startup time nicely. So again, basically the idea here is just doing fewer disk operations. Another thing worth mentioning maybe is, before we move on, is Windows Superfetch. And this really isn't something you have lots of control over, but it's worth mentioning because you can disable it completely, and that happens occasionally in certain environments. Windows Superfetch is a mechanism built into Windows since Windows Vista or so. Yeah, Windows Vista, I think. It takes your memory, it takes your disk accesses performed over the last few runs and tries to predict which disk accesses you're going to need the next time. So for example, next time you run your application, it tries to use historic information about disk accesses to see which disk pages you're going to need next. And again, it's kind of a background thing. So while your application is starting up, Windows is trying to guess which disk accesses it's going to need and makes those disk operations in the background. Now, you usually don't see Superfetch having any effect on your system, except for taking a little more memory and maybe doing occasional disk accesses, which you didn't expect. But some people still turn it off. Some system administrators turn off the service that does this, with the Windows Superfetch service. If you see it turned off, could be worth trying turning it on. Again, for certain kinds of applications, it can predict quite well which disk pages you're going to need, and then it can save you those file accesses at the most inconvenient time. So whenever your application needs that page, it will already be loaded into memory. By the way, Superfetch theoretically has even more sophisticated capabilities. For example, it could theoretically predict that at 12 p.m. you leave your desk and go, go to lunch, and then at 1 p.m. sharp you come back and open Outlook. And so it can predict that at 5 minutes to 1, it should start reading your email files from disk because you're going to open Outlook soon, right? It's part of Windows, this thing, but I mean, that's kind of stretching it. But for startup, for standard, regular startup, when you just access pretty much the same things on disk every time, Superfetch should have some effect. And by the way, before Superfetch, Windows used to have a mechanism called prefetch, Windows prefetch, which was available since Windows XP, which also had a nice effect on performance, and Superfetch is just an evolution of that. So in case you've heard of prefetch, that's the logical next thing. Okay, so that's for startup anyway. There's a bunch of little ways that can affect startup times, and now we're going to take a look at a few things that will affect worm startup as well. Let me just... okay. So two other things we're going to look at are precompiling things which aren't your main .NET assemblies, but other things that your code might be using and that can be precompiled in advance. One of these is serialization assemblies. In many serialization frameworks, such as data contract serializer, binary formatter, XML serializer, a bunch of others that you might be using, in many serialization frameworks, there is a compilation step the first time you try to serialize or deserialize a specific type. So for each type, the framework has to generate a couple of methods, occasionally a whole class, that will do the serialization at runtime. Now, it's obviously important to do this compilation at runtime. You can throw any type at a serialization framework, and it has to be able to react. But the problem is that the first time you try to serialize something or deserialize something, you're going to pay the cost of this dynamic compilation step. So here's a hypothetical example. Suppose the first time you serialize an instance of my class, your serialization framework has to emit this kind of little dynamic method, which takes an instance of your class and a binary writer and spits out the different fields of your class into that binary writer. So it's not a lot of code, but it has to be compiled. It has to be, emitted and then compiled at runtime. So it can take a few milliseconds and occasionally a lot more. These methods can and should, if you can, be precompiled. For example, with XML serializer, there is a built-in tool, part of the framework, called sgen.exe, which can take a set of types and generate the serialization code in advance. It will generate actual assemblies on disk, which you can then reference from your application instead of having to generate them on every run at runtime. So that's for XML serializer. You're asking about other serialization frameworks. Well, some of them have similar tools, some of them don't. For example, Protobuf, which is a really great Google library for data serialization, Protobuf has a precompilation tool as well, which you can run in advance, and it will generate all the serialization code for you, so you don't have to pay for it at runtime. So some frameworks have it, some frameworks don't. And this is another piece of work that you can save at runtime. And this, again, affects worm startup because you're doing it every time. Every time you launch your application, you have to generate and compile these serialization assemblies. Another very similar example, in the same spirit, is regular expressions. I assume some of you are using regular expressions in your .NET code today. And the regular expressions, the standard engine employed by the regex class uses interpretation. So it looks at your regular expression, and it doesn't generate any dynamic code. It just parses your regular expression, and then it tries to execute it, at runtime without generating any specific code. So basically like a script interpreter. But regex also has a simple constructor overload, which takes regex options compiled, which means instead of interpretation, it's going to take your pattern, it's going to take your regular expression, and compile it down to dynamic code, pretty much like the serialization example I've just shown you. So this occasionally is better in terms of runtime, but it does slow down a little the startup process. But you can enjoy the best of both worlds by precompiling your regular expressions to an assembly. And that's something you can do. It does require a little more work. There's a regex compilation info class, and the regex class has a static method compiled to assembly. And this can take a regular expression and compile it down to an assembly. So you do this once, say, in a little console application, and then you can reference that assembly and use it at runtime to match your regular expressions. So this means the regex itself is going to be faster, and it also means your application will start up faster because it doesn't have to generate any code during runtime. You can even run nggen on those little assemblies. So let me just show you a quick example of how regex parsing can be made faster by using precompilation. So I have two regular expressions here for matching email addresses. I thought that would be a classic example for using regexes. And the simple pattern goes like this. Well, regular expressions tend to be unreadable no matter how you write them, but this one is relatively simple. Basically says we have letters, digits, and a couple of special characters, any number of those, followed by an @, and then again letters and digits, dot, and then again letters and digits. Obviously, it doesn't catch everything, but it's good enough for many websites. The more complex regular expression, which I've stolen from some website, goes like this, and it's slightly longer at 182 columns, and it tries to capture almost everything specified by the email RFC. So what I'm doing here is trying the standard regex, the simple regex with and without pre-compilation. So that's what the results look like for the simple email regular expression, and compiling it makes it quite a bit faster. But if we try the real one, the difference becomes even more apparent. Should be about twice as fast with the compiled version. Now, what I'm showing you here is that compiling the regex, as opposed to interpreting it, can make matching much faster. But if you're compiling it at runtime, then you're losing startup time. So again, like I said, you should consider doing both by pre-compiling your regular expressions to an assembly. That means there is no interpretation at runtime, and it also means there's no compiling going on at runtime. And this is the best of both worlds. It does mean that you have to identify regular expressions which are worth doing this for. So if you have thousands of regular expressions you use, you're not going to do that for every one. But the key ones which your profiler shows you can make this worthwhile. So that's all different things we can do that have to do with pre-compilation and improving startup. And we have time for one more, actually, and then we'll talk about GC as well. No, I think we'll talk about GC first, because I really want to make sure I have time for a couple of demos here as well. So I'm going to talk about GC pressure a little now. And this is also an extremely important part of making your applications faster. It affects pretty much every kind of application, again, web apps, console apps, WCF services, client applications of any kind. The garbage collector is a key component of the CLR, and if you can make your interactions with it faster, you can almost always improve performance. And there's a few things I'd like to show you through a series of simple demos. In general, when dealing with the garbage collector, your most important tool should be some kind of profiler. You should not be just making assumptions. And I'm going to be making assumptions. I'm going to be showing you complete pieces of code that I improved by changing a particular aspect of the code. But you shouldn't be just trying out all these things at random. You should use performance tools which can tell you whether and where the GC is a performance issue in your application. And there's a bunch of tools for that. You have Windows performance counters, which can tell you very basic things like the amount of time you're spending in the garbage collector, or the total memory usage of your application, or how many garbage collections you have over time. I'm not going to show you the tools, but it's important to mention that they exist. The other thing you can use is ETW, event tracing for Windows. And I will show you momentarily a simple tool that you can run and get lots and lots of information from the CLR on memory allocations, garbage collection statistics, the amount of memory you're allocating in every given method, lots of information that's important for reducing garbage collection pressure. And if you see there is an issue to give your attention to, then you should try some of the approaches I'm going to talk about here. So one obvious thing, hopefully obvious, is using smaller types, using smaller objects. The smaller your objects are, the less memory you're using. Less memory means less work for the garbage collector. And one of the key ways in the CLR we have for reducing object size is by making objects values, making objects that are reference types value types instead. And the key reason is as follows. If you take a couple of types which are structurally equivalent, but one is a class and one is a struct, so one is a reference type and one is a value type, the value type is just going to have its fields consecutive in memory, no additional overhead, exactly the way the data was arranged by you. In a class, on the other hand, there's per object overhead, which I've already mentioned before when we talked about collections. And this per object overhead on a 64-bit system, again, that's 16 bytes right here. And that's 16 bytes the garbage collector has to take care of. And it becomes even worse if you put these things in containers. So if you have a container of these structs, then they're just arranged consecutively in memory, x after y, x after y, well, actually y after x, y after x. On the other hand, if you have reference types arranged in a container, then what you really have in that container are references. And each reference points to a heap object which has the object overhead fields plus your x and y fields of your point type. And the difference can be really, really bad and big for the GC. So let me show you a quick example. Again, it's kind of engineered to emphasize the key parts, but it is a kind of a real algorithm which value and reference types can affect. So what I have here is a simple console application which calculates and prints the Mandelbrot fractal. If you were at one of my other talks, I had a GUI app which does the same. This is a console version, ASCII art. I like my console applications that way. So it does some calculation and generates a nice image. Now, I have two versions of every class used by this application. I have point C and point S. I have a Mandelbrot C and Mandelbrot S, and I have a complex C and a complex S. The C ones are classes, the S ones are structs. And just to show you the code, let's take complex, for example. So here's class complex C. It's a class, and it's got the two components of a complex number inside. That's the whole thing in memory. And here's the complex S struct. Same thing, same operations. Now let's take a look at point. So here's class point C, and here's struct point S. Again, they both just have int x, int y, the point's coordinates, and other than that, the code is almost identical. And finally, the Mandelbrot C and Mandelbrot S classes use these other types. So they use lots and lots of points, and they use lots and lots of complex numbers. And what the benchmark does is just compare the two approaches. So take a look. I pressed enter. OK, so by using structs, just mechanically switching classes to structs in this particular contrived example, I was able to bring the runtime down from 5.5 seconds to 3.2 seconds, which is really great. Plus, I was able to bring down the number of garbage collections from 2,600 garbage collections to 3. That's generation 0. There's also collection numbers in the other generations, which are similarly impressive. And finally, I was able to bring down the working set, the amount of memory used by this application, down from 42 megabytes to 32 megabytes. And that includes everything. It's not just the things this algorithm uses. So just by using value types, we were able to shave off 10 megabytes of space and a considerable portion of the running time. Now, again, I realize you can't just blindly replace every class with a struct, and that's not what I'm saying. What I am saying is that you should look for the types that really have to be value types if you want them to be successful, if you want them to be performant. And here are the simple rules. If you have a small type, which doesn't have lots and lots of fields, and you plan to create lots of instances of that type, then it probably should be a value type. And things like points and complex numbers, coordinates, all kinds of numbers or bigger numbers. These are all things that you should definitely consider making value types. And if you're building libraries, it's even more important, because if you build your library around reference types up front, it's going to be really hard for your users to make this sort of transition later. So consider using value types when appropriate. It can really bring down your GC pressure. It reduces running time. It reduces memory usage, all of which are important for modern applications. Now, another thing you should obviously consider, other than using value types, is just getting rid of unnecessary allocations, trying to reduce the amount of memory your application is allocating in general. And I'm not going to show you a concrete example, but I do want to show you that we have tools to pinpoint this kind of thing. So you don't have to blindly guess, well, here I'm allocating a big object, let's try to get rid of that. You can use tools that tell you where and what you're allocating. And one such tool is perfview. It's a fairly new tool. It's been around for a couple of years or so, maybe 3. And it can measure allocation sources accurately. It can tell you where exactly you're allocating memory, which types you're allocating, and how much pressure this is putting on the GC. So perfview, if I just run it here, perfview is a really simple, not very user-friendly tool, which looks like this. Let me just switch to my temp folder over here. And you can tell perfview to run a specific application and collect allocation information, or to collect allocation statistics from an already running process. So I'm going to do that with Visual Studio. I have a Visual Studio instance open. I'm going to try and see where Visual Studio is allocating managed memory. So I'm going to do collect. And I'm going to tell perfview to collect into the c/temp folder. And in this horrendous advanced options dialog, I'm going to say that I'm interested in .NET sample allocations. And I don't really need CPU samples. I'm not explaining everything, but it's a tool that has a great tutorial. So I'm just want to show you the key parts. It's free, by the way, in case I haven't mentioned it. So it's running now. Let me just pick one of my Visual Studio instances and do something. Maybe, OK, let's try to open the NuGet package manager. OK, so I'm opening it, and it's done something, and I'm going to search online for something else. OK, so hopefully a couple of allocations were made. Going back to perfview, I'm going to stop collection, go back to perfview. It has this thing where it loses focus, and wait for collection to complete. Once it's done, I have this file over here. I think that's the one I just created, alloxedl. Let me just make sure. alloxedl, no, that's not the one. Where's the one from right now? This is the one, perfview data ETL. OK. There it is, perfview data ETL. And under this report, there's a bunch of subgraphs which I can review. So first thing I want to show you real quick is what perfview can show you for GC statistics. By GC statistics, it means basic stuff about the garbage collector's behavior, but also individual garbage collection information. So if I double-click this report, I get this, which is an HTML page hosted inside a mini browser. That's the way perfview rolls. And for each process over here, let me just scroll this thing. It doesn't scroll for some reason. Loses focus or something. So for each process, it gives me basic information such as the percentage of time paused for garbage collection, so when and how the garbage collector suspended my process, the maximum heap size, allocations, allocation rate, all kinds of basic statistics like that sort of help you understand if you can really improve performance by reducing allocations. If you don't know you have lots of allocations, you can't really improve performance. Down here, later in the report, there is also this table for individual garbage collection events. So it's a table where each row is an individual garbage collection, and you can see the timestamp when that collection occurred, what kind of collection it was in terms of generations and stuff like that, and also the duration of the GC, how long the garbage collection was. So if you have long garbage collections, again, it might be worthwhile looking into reducing allocations. Otherwise, it's just not really relevant for you. And the nice part is that if you know you have allocations to reduce, if you know you have pressure that you can remove, then you can look into the GC heap allocations report, which will give you detailed information on where you're making object allocations in your app. So if I double-click this report, I can now pick a process, and it's not going to be easy to pick the right one, so let me try. I have multiple Visual Studio instances, but, oh, and the titles aren't, or are there? Oh, they are. So the one I'm looking for is probably the last one. Yeah, the built-in collections one. And can you kind of go to the process, please? Go to details. OK, so that's 7576. OK, now let's try to find a process with that ID over here, 7576. OK, so here's the Visual Studio that I was really interacting with. I'm going to double-click it. OK, that's a wording I can live with. And next thing I get is a detailed report that says which objects my Visual Studio was allocating while I was playing around with that NuGet package manager. And specifically, it says that strings I have a lot of, namely 11.2% of my allocations were strings, which isn't really that surprising. And in numbers, it's just over 3.5 megabytes of strings. Next up is arrays of event key, and then arrays of bytes, and so on and so forth. So you can tell exactly which objects you're allocating, and not just that you're allocating lots of memory. And you can drill even further. I'm going to show you just one basic example. I can double-click a type here and see call stacks which are responsible for allocations of that type. I'm not going to drill into the table, the tree here. Also, some parts of it are broken, and I need to load symbols for it to work. But just briefly, you can understand where in code you're allocating those strings. So you start from the general GC report, which just gives you basic information on allocation rates. And then you have the types that your application is allocating. And finally, you can see which methods are allocating those types, which can really help in reducing pressure again. The techniques for doing so can really vary from one scenario to another, but there are a couple of general guidelines that I can share with you. One basic idea is buffering, so taking lots of small allocations and trying to turn them into a bigger one. And this is, for example, what String Builder does. And that's a classic optimization for memory usage. Instead of concatenating lots of small strings, you can use String Builder, which does a big allocation and then sort of increases the usage of that one big allocation. So that's one idea, a general shape of a pattern of a solution. The other idea is kind of the other way around. Instead of making allocations at all, you can pool objects which you have once allocated and not reclaim them. Instead, you can just keep them in some kind of collection and reuse them as necessary. And this is something that WCF uses as an example. WCF has an internal class called Buffer Manager, which does this kind of pooling for large buffers. It takes large buffers used for serialization and for sending out messages, receiving messages, and it doesn't give them back to the GC. It keeps them in a nice little pool, and whenever a buffer is required, it just gives you a buffer from the pool. And it's obviously quite simple to implement yourself, but the one that WCF is using is not exposed. It's internal. But without this kind of optimization, WCF would end up making lots and lots of large buffer allocations and spending a lot of time in the garbage collector. in an area that you don't have control over because you don't have access to WCF's source code yet. So buffer manager is just one example of pooling allocations instead of giving them back to the GC. So these are the general techniques for taking care of these issues, but the key part is you have to measure and understand which objects are worth taking care of. And we have tools for that today. So we do have time for one final demo, which I really wanted to show you. Oops, missed the slide. And that's a demo on finalization. And it doesn't really have a lot to do with performance, the demo I want to show you, but it is kind of important, I think, and will show that understanding internals and understanding how the system works can be really, really valuable in some situations. So in general, finalization is a really bad thing. And if you can, please don't use finalization like ever. Unfortunately, some of us are stuck with finalization because you use existing classes that have finalizers, or you might be maintaining code that has finalizers, or you're just using the .NET framework, which has classes that have finalizers. But finalization is bad for multiple reasons, and I'd just like to show you one such reason, which is really subtle. But it also has lots to do with performance, which we don't have time for right now. So here's the demo I want to show you, and this really should drive home the point that finalization is a horrible, horrible thing. So here's a super trivial application. I have here my own custom homemade file class, because that's what I want. And then my main program creates a file, reads 200 bytes from the file, and displays a string based on those bytes. I just hand-rolled my own file class. Now, if I run this thing in debug mode, then it runs really great and prints out some junk from the file. If I run it under a debugger, it runs to completion and prints out whatever it was supposed to print out. But if I run it in release mode without a debugger, then unfortunately it crashes. And the way it crashes is also kind of annoying. It says, warning, attempting to use a closed handle, and then there's an unhandled exception, Win32 exception, error reading from file, and I get a call stack. And this is the kind of thing you waste time on and lose hair over and sleep and healthy things, because it works in debug mode, it works with a debugger attached, it doesn't work in release mode when there isn't a debugger attached. So it could be a timing issue maybe, or some voodoo thingy from the internals of the CLR. But it's really all related to finalization. The incredible thing is that when you're using finalization, there's now multiple threads touching your objects when previously there was only one. And so let's take a look at this particular situation. I just want to remind you of the exception we get. We get this warning here, attempting to use a closed handle, and then an exception with an error reading from file. So let's see where this is coming from in code. The warning message is here. I have a handle class, which represents a handle to a file, and it has a use method which emits this warning. So if the handle is closed, then the use method will emit a warning. Probably should have thrown an exception, but that's what it does. It prints out a warning if the handle has already been closed. Next up, we have the file utilities class, which throws the exception we're seeing. So right over here, it tries to read from the file, and if it fails, and it fails, it throws that Win32 exception that we have just seen. Now, there is a hidden region here, but I guarantee, the comment guarantees, that it doesn't close the handle, right? So it's not deliberately closing the handle in release mode. It's just there for a particular reason. But by the time we read from the file, the handle is apparently already closed. And it's only happening in release mode, and it's only happening when there isn't a debugger attached. And the obvious thing to do is to see who is closing that handle. I mean, look for callers of handle.close. And conveniently, there's just one reference to handle.close. And here it is. it's in the finalizer of the file class. No one else ever calls handle.close. So the finalizer of the file class closes the handle, which sort of makes sense. We have to clean up resources. No one else ever closes that handle. And if you look at the program code, the program creates a file class, and then the file class dies and goes away. So naturally, at some point, the handle should be closed, but not while we're reading from it, right? So the incredible outcome, if you haven't followed all the little details along, the incredible outcome is that we are still reading from that file, and the handle is getting closed as we are reading from the file. So in other words, where's the file class? In other words, the finalizer of the file class is being called while we are still reading from that very file instance. And this is something that can happen with finalization, unfortunately. It is not a CLR bug. It is not a versioning issue with the .NET framework that you have to install a patch to fix. It is a core feature of finalization. That's what you get. It is possible for your finalizer to be invoked while there is still a method on your class that hasn't returned. And in our case specifically, there is a method on the file class which hasn't returned. It's still stuck right here. And at the same time, the finalizer is being called. Now, why does it only happen in release mode? Why doesn't it happen when there is a debugger attached? There is a reason for that, but I'm going to keep you in the dark about that. If you are interested in the details, there's lots of good information about that online, including on my blog. But the core issue, again, is you have a finalizer that's being called while a method on that class is still in progress. And there are multiple ways to take care of this. One way you'll laugh at, but it works. I can take the file class and, I don't know, call to string at the end of main, for example. And this, in a totally insane fashion, will convince, somehow, the CLR that it isn't possible to call the finalizer while the read method is still executing. So as you can see, it now works successfully without a debugger attached in release mode. If that looks like a voodoo, consider another possible fix. I can also go to the file class and sort of reorganize this thing a little bit. I could put a this to string call over here as well. And it also fixes the problem. So it's like, putting random statements across your program can make it work. Not the kind of thing you want in your production application. And this is, again, a key feature of finalization. I'm obviously stretching this a little, but it is a key problem with finalization. The decent way to address this kind of problem is just to avoid finalization. The problem here is that the finalizer runs in a separate thread. So it touches the object while another method on it is still running. But if we use the dispose pattern instead, which is what you're supposed to use anyway instead of finalization in .NET applications, then this problem isn't only going away, it simply couldn't have been there in the first place. So here's another possible fix, briefly. Oh, man. I make my file class implement the iDisposable interface. I'll give you all the code later, so you don't have to copy it. And in my dispose method, I will then close the handle. I will remove the finalizer for this particular instance. And in main, I'll use a using statement to read from the file. Now, I can guarantee deterministically that the file is getting closed right here, and so the handle is getting closed right here, and this is strictly after I'm done reading from the file, because it's on the same thread. So we get here only after the read call has returned, so there is no way the handle is getting closed while we are still reading from the file. There is just one thread, and it would violate data dependencies. And so, again, with this refactoring, everything works fine in release mode, without a debugger attached, and with a debugger attached. We have eliminated the source of randomness or non-determinism, if you will. So finalization is dangerous, and it's bad in terms of bugs, like the one I've just shown you here, but it also has horrible effects on performance, which I haven't illustrated here. For example, finalization means objects survive longer. Finalization can create temporary memory leaks. There's lots of other issues that we could have talked about, but we don't quite have time for. So I would like to wrap up, and if you have a couple of last-minute questions, it would be appropriate. So there were 3 core topics I tried to show you here that have to do with making .NET applications faster. One was choosing the right collection, or even writing your own one. And I mean, the example we saw are rather naive, but still, they demonstrate that space complexity matters, running time complexity matters, and in some cases, you can come up with this genius super collection that makes your scenario shine, and no one else is going to find any use for. And it's worth thinking whether there is a use case for a custom collection like that. Second thing is startup time, and we saw a variety of ways to improve startup times, pre-compiling your whole program, pre-compiling serialization assemblies and regular expressions, and a bunch of new technologies like multi-core background JIT and the new just-in-time compiler, all focused on reducing startup times for .NET applications, because it's really becoming a problem for both server and client apps. And finally, for GC, the garbage collector is a key component of almost every .NET system, and you can measure the GC's effect on your system. You can see how much time you're spending in GC, how much allocations you're making, how many allocations you're making, and you can see where they're coming from, where in code you are making heavy allocations. There are tools for that. And then you can reduce pressure on the GC by making fewer allocations, by using value types if appropriate, and lastly, by not using finalization if possible. Like I said in the beginning, if you'd like to hear more, this was just a preview. There's lots of additional material available online and courses and books. And if you'd like any references, of course, then I'll be happy to share some with you. And again, if you'd like Pluralsight trial cards, there's the booth, and they'll be happy to share some with you, especially if you mention that you've just heard about .NET Performance and you'd like to hear more. They'll be ecstatic. So I hope you've enjoyed this and that you'll enjoy the rest of the conference as well. Right after this one, I have a talk on C#6, which is a totally different topic, C# features new in Visual Studio 2015. And if you have any questions, I think we have 2 minutes, so I'd be happy to answer. I'm just going to put up the slides with my contact details. Yes, sir.
What do you think about some of the advantages and pitfalls of using the low latency mode of the garbage collector?
What are the advantages of what?
The low latency mode of garbage collector.
Low latency mode. Low latency mode, right? That's what you're asking? OK, so just to make sure everyone knows what it is, low latency mode is a way to tell the garbage collector that you'd like to, if possible, not do any heavy garbage collection at all until you say it's OK. If you're using the older flavor, the low latency mode that was available since .NET 3.5, it's good only for short intervals. It has really bad effects if you keep it on for a while. But in .NET 4.5.1, I think, they've introduced a sustained low latency mode, which helps you tell the GC, I want very low GC all the time. And that's a reasonable option to keep on for a while. In any case, it's not reducing pressure on the GC. You're just instructing the GC that you're willing to spend more memory and that you're willing to sacrifice performance elsewhere. So, I mean, you're still doing the same amount of allocations. You're still putting the same pressure on it. Huh?
Purview is really usable, is it?
What's that?
Purview?
Purview, yeah.
It's not really usable. Do you have any recommendations?
It isn't very usable?
Well,
Yeah, well, it's free. It's very small. You can use it in production. These are great advantages. But yes, the user interface is bad. Specifically for allocations, yes, there are other tools. But something as holistic as Purview, there is no other tool. Something that can do system-wide measurement, that doesn't intrude into the process, doesn't inject anything. it's a great tool, but yeah, for allocation specifically, yeah, you've got Visual Studio Profiler, you have the JetBrains tools, you have the Redgate tools. They can all do pretty much the same for just reducing allocations specifically, yeah. Yeah, and they also have a nicer UI and all. Okay. Okay, well, if you have any other questions, then please feel free to approach. I'm going to stay here anyway for the next session. So thank you very much for coming. Enjoy the rest of DevWeek. Thank you. Quick demo comparing trees to hash tables on the next slide. One of the key problems with trees is that you still need lots of space for each element. So each tree node has a link to the left child and the right child, plus it has a link to the parent in the .NET implementation. So that's 3 pointers already for each node. 3 pointers, that's 24 bytes on a 64-bit system. Plus, each node is a reference type. So you also have 16 bytes of object overhead. So that's already 40 bytes of overhead. And then you have your elements. And then you have the stuff you want sitting in the tree. So that's lots and lots of space that's wasted. And again, if I were to implement some kind of algorithm that goes over a tree and sums all the elements, it would have been, again, much slower than doing the same thing with an array because of this whole sequential property that arrays have. So the other kind of associative collection that we have in the .NET framework are hash tables of various kinds. So we have dictionary of key value, hash set of key, and we also have the hash table class, the old one, the non-generic one, which no one should be using anymore, but it's still out there. And these classes are somewhat more complex internally to describe. They use a variety of arrays to store the data. There are also some linked lists inside. So it's harder to estimate exactly how much space you're sacrificing for the more efficient operation of those collections. It's probably somewhere between a tree and an array, probably closer to a tree. So you're spending quite a bit of overhead for each element still in those hash table-based collections. In terms of runtime, however, you have insertion, deletion, and lookup in constant time. And that sounds like a great property, which it is. It does require some discipline from you as the developer. You have to make sure some constraints hold for your hashing function, for your get hash code implementation. We're not going to go into detail here, but assuming you've got that right, or you're using a common type as the key, such as a string or an int, other primitive types, assuming these hold, you get a really efficient collection in terms of lookup and insertion and deletion. The one thing it does not guarantee is sortedness. It is not sorted by anything, which could, in some cases, be important. So let's take a look at a quick demo, again, just to see how big the difference can be between logarithmic time operations, hash tables, which are sort of the best, and linear time. So again, I have a very simple demo just to drive this point home, which searches a range of elements for a specific element which isn't there. So in one example, it's nodes, the links, I mean. And again, on a 64-bit system, each is 8 bytes. So these are another 16 bytes. And then finally, we have that, the data that we want to store in the linked list. And if you're storing, say, ints, then each int is only 4 bytes. So this whole thing is going to be 36 bytes on a 64-bit system. And only 4 of those bytes are the actual data that you put in there. So there's definitely something interesting if you look at collections from a space complexity perspective. And I'm going to show you a very quick demo just in a moment. The other things, the other operations are pretty quick. So it's really easy to insert and delete elements because you always have these links between the nodes. But lookup is slow. There's no built-in way to index into the collection to find an element by key. You just have to go linearly through the whole thing and compare whatever you're looking for. The other kind of collection, which is a foundation for lots of others, including one we're going to build together, is, of course, the built-in arrays. And arrays are great. They're flat. They're sequential, so all elements sit together in memory. However, they are statically sized, so you can't add or remove elements anywhere. You can just change the existing ones. It is almost an immediate operation to access an element in an array by index, which is something you can't do with a linked list. And there is, again, no overhead for the array elements. So if you have an array of 1,000,000 ints, you can very quickly just, you can in very little space store those 1,000,000 ints. You're not wasting any space on object overhead, nodes to the previous and next elements, and so on. So let's take a look at a really, really simple demo, which tries to compare two very fundamental operations on arrays and linked list. So what I'm doing here is basically creating an array of a certain number of elements and creating a list, a linked list, with the same number of elements, and then measuring the time it takes to sum all the elements in both collections. So here's one loop I'm measuring. It just goes over all the elements in the array and sums them up. And here's the other loop I'm measuring. It goes over all the elements in the linked list and sums them up. So I hope you all expect there to be a certain performance difference, because I've just explained how lists are big and wasteful, and there's links going here and there, and it's so much more efficient to use an array. But how many of you think it's going to be a significant difference, like a big, big difference? OK, so I phrased the question correctly. Let's run this thing. It does lots of iterations to make sure there's no weird outliers. And it takes almost 3 times the time, such as hash set, which was only added, I think, in .NET 3.5. And there's all kinds of concurrent collections being added more recently. So there's still lots of work on the .NET Framework's collections library, which sounds really fundamental, but there's still some additions going on. In addition, there are many good, even excellent, production quality libraries for .NET applications which have even more collection implementations. For example, there's the C5 library. Has anyone ever used C5? That's wonderful. So C5 is a really great library that has implementations for pretty much everything you find in an algorithms and data structures book. Plus, it has some specialized collections. And they usually are very rigorous about giving you, the asymptotic guarantees and sort of documenting every little detail, even better at that than the .NET Framework collections occasionally. But in any case, for all of those built-in collections and for any library you find, the fundamental operations on a collection are usually inserting elements, looking up elements by some criteria, maybe by key or some other way, and of course deleting elements from the collection. But the differences between the different collection classes, as I hope you know, are first, runtime complexity of the different operations. So how long does it take to find an element in a collection by key or insert an element in the middle of a collection? Space complexity, which means the space, the memory usage of the collection given a certain number of elements, and these vary greatly. Some collections could be a dozen times bigger than others for the same number of elements. And then we have specialized operations. Some collections make it possible to do certain things very, very efficiently, while others don't. And I'm going to show you one example of that as soon as we get through the fundamental collections, which are part of the .NET Framework. We're going to take a look at an example where the operation we need is unique and is not implemented by any existing collection in the BCL, and we'll have to sort of roll our own. So let's take a look at one simple example, then review a few others, see a quick demo, and this should give us a good coverage of the built-in collections anyway. So here's linked list of T. And if you ever looked at the structure of a linked list, specifically the .NET implementation at runtime, it's a pretty big object. It's got lots of little objects inside, but each object is pretty big. So this is a typical node in a linked list of T, the .NET class. It has a couple of overhead fields which are there regardless of the type of object you're allocating. This is the overhead that every .NET reference type has. So we're not going to go in depth here, but these are the object header word and the method table pointer. And for instance, on a 64-bit system, these are 16 bytes together. And then we have the next and previous to sum a linked list than an array. And it's not like there are more operations involved. It is the memory structure. It is the space complexity that kills us here. If you look at the generated assembly language, if you're the kind of person who likes to look at the generated assembly language, you'll see the basic operations are pretty much almost the same in both cases. But it's the fact that you have to touch more memory that's killing us in the linked list case. You have to touch more memory, which means you have to go to memory more often, and the cache doesn't help you as much. If you'd like me to go into more detail, please feel free to ask me later. But for now, let's just agree that space complexity matters. So not the only I mean, you should be looking at more than just the O of whatever guarantees for runtime complexity. You should also be looking at space complexity as a criterion for your collections. And arrays are often really good at this. Right? Arrays often beat other collections in space complexity because there is no overhead except for the array elements and a tiny, teeny header that the whole array shares. It's not a per element overhead. So anyway, that was just a quick demonstration of space complexity. I would like to also show you an example of how the different collections differ in terms of runtime complexity, which is going to be more obvious, but still it's important to see just how big this difference can be in terms of running time. So I'm going to skip ahead a little bit to trees and hash tables, just again to give you a quick coverage of those. We have a couple of collections in the .NET framework which are based on binary search trees. Specifically, the .NET implementation uses red-black trees, if you recall from school or an algorithms book. There used to be implementation based on AVL trees, but red-black trees are pretty much the state-of-the-art for binary search tree collections today. For example, the C++ standard library uses red-black trees as well. And so sorted dictionary and sorted set are just trees like that, and they give you fairly efficient lookup by key, and also they are sorted by key, which is something extra, right? I mean, we talked about space complexity, we talked about runtime complexity, but the fact the elements are sorted just comes extra. It's just another property of the collection, which we occasionally might need. All the fundamental operations on trees take log n time, log-based 2, which means really little time in most cases. So for instance, log-based 2 of 100 million is just a little less than 27. So, 27 operations in the tree for a tree of 100 million elements really doesn't sound like a lot. But it still does matter if you have lots of these operations, and I'm going to give you a Well, OK, so I guess we can get started. Again, the beautiful acoustics of this hall. I mean, I'm not using any, I think, enhancement. So welcome to this talk on making .NET applications faster. I hope you're enjoying the conference, and I'll try to keep up the trend. We're going to talk about some best practices and techniques for making .NET applications, faster. And these tips and demos are built on a large body of work that you can also see in my Pluralsight courses. And by the way, if you'd like a trial Pluralsight subscription, there's a booth, and they'll be happy to hook you up with one. And there's also a book I wrote a couple of years ago called Pro.NET Performance, which might also be useful. But here I kind of try to take the whole book and the 2 courses that I have on .NET Performance and just sort of distill them into the most useful things that I could fit in 90 minutes or so. We're going to talk about reducing garbage collection pressure to improve runtime and to improve memory utilization. We'll talk about reducing startup times, which in many applications is quite critical. For any kind of client app, it's really important to reduce startup. And even for server applications, longer startup means you spend more time, not servicing requests, especially if something fails. And we'll also talk about collections, the .NET built-in collections, and how to choose some more sophisticated collections, even implement your own collections if the situation requires it. So some of these things are more basic and some are more advanced. For example, the whole collection discussion, I'm going to go through it really briefly because I think many of you as .NET developers are already familiar with the various kinds of collections we have. But the other things could be a little more advanced, and there's one demo at the end, which if we have time to get to, it's going to be great. It's a really crazy one. My name is Sasha Goldshtein. I live in Israel. I work for a company called Sela, which is a training and consulting provider. And this is my third DevWeek. I'm having fun. I hope you are too. And right after this talk, I'm staying here for another one on C#6, so you're also welcome to stay. So as I said, we're going to talk about collections, startup time, and garbage collection. These are three core topics, and there's lots of little things around. So let's start with collections, and like I said, it's going to be a pretty quick review. The .NET framework has a bunch of collection classes, and new ones are being added all the time. For instance, in .NET 4.0, we had multiple collections made available in the concurrency framework, in the TPL. And previously, we had additions